Let's get right into it. Today, we're diving into one of the most fascinating, ambitious, and honestly awe-inspiring technological pursuits in human history. We are unpacking the complete history, the hardcore science, and the breathtaking future of nuclear space propulsion in this explainer. We're going to see how humanity went from the earliest theoretical concepts born right out of the atomic age all the way to the modern revival that's aimed at taking us to Mars and beyond.
You know, the great astronomer Carl Sagan once made this profound observation about time dilation at immense speeds. But beyond that, he was also a huge advocate for advanced nuclear propulsion systems. Because, well, the harsh reality of space is that it is unimaginably vast. If we actually want to cross those cosmic distances, to truly travel fast into the future, we have to completely rethink how we generate thrust.
Section 1. The Nuclear Rocket Promise.
To understand why this matters, think about our absolute best chemical engine right now, the RL-10, and compare it to a notional nuclear thermal engine designed for a Mars trip. The thrust they produce is practically identical, right around 25,000 pounds of force. But look at the efficiency. The nuclear engine delivers roughly double the performance. Basically, it gives us the exact same push, but uses half the propellant to get the job done.
So what's the secret sauce here? Well, it comes down to a metric called specific impulse, or ISP. It's essentially the spaceflight equivalent of miles per gallon. See, in a normal chemical rocket, you mix fuel and oxidizer, right? That creates heavy combustion byproducts, like water vapor or carbon dioxide, and that heavy exhaust fundamentally limits your specific impulse. But with a nuclear engine, there's literally zero combustion. You just use pure hydrogen. And because hydrogen has the lowest molecular weight of any element in the universe, heating it up and blasting it out the back optimizes this specific impulse metric perfectly.
Moving on to Section 2, how nuclear propulsion works.
Okay, so how do we actually get physical thrust from an atom in a vacuum? The heart of the system relies on a controlled fission chain reaction completely identical in principle to what powers terrestrial nuclear power plants down here on Earth. Typically, you take a fissile material like uranium-235, bombard it with neutrons, and the atoms split apart. This releases more neutrons to keep the chain going, but more importantly, it generates an immense, intense amount of heat. We aren't creating an explosive blast here, we're creating an ultra-high temperature heat source.
Inside the engine itself, that traditional chemical combustion chamber is completely replaced by a solid nuclear reactor core. Liquid hydrogen gets pumped straight from the tanks and flows right through channels inside this intensely hot, fissioning core. The hydrogen heats up drastically, expands violently, and just shoots out the nozzle at the bottom. It generates massive thrust, and it does the whole thing without a single drop of fuel ever catching fire. Which brings us to Section 3, the Golden Age of NERVA.
Now you might think this is all futuristic sci-fi, but this timeline maps out an incredible, yet somehow totally forgotten piece of history. It actually started way back in 1955 with Project Rover at the Los Alamos lab, using concepts straight from Manhattan Project scientists. By 1958, a newly formed NASA stepped up to develop it for civilian spaceflight. That all culminated in 1968 with the incredibly successful testing of the XC engine, which was practically ready to fly. But, as we'll see, the program was ultimately terminated in 1973.
The sheer scale of this effort during the space race was just mind-blowing. First, the Kiwi series proved the basic physics. Then, the Phoebus reactors cranked the power up to unbelievable levels. And finally, the NERVA NRX and XE programs. These weren't just theories on a chalkboard. They actually built them. They fired them up in the Nevada desert. They proved without a doubt that nuclear engines could be reliably started, run at full power, shut down, and successfully restarted multiple times.
All right, Section 4, Engineering Challenges and Risks.
Now, obviously, putting a nuclear reactor into orbit isn't exactly a walk in the park. Beyond the crazy engineering hurdles, like figuring out how to build a core that won't just melt when it operates hotter than a standard chemical rocket flame, there are some severe physical penalties. Liquid hydrogen is super light, but it takes up a lot of space, meaning you need fuel tanks up to 3 times larger than normal. Plus, these engines become highly radioactive once you turn them on. That means you need heavy radiation shielding, stuff like tungsten or lithium hydride, just to protect the astronauts and the payload, which slaps a ton of significant weight right back onto the spacecraft.
So if it worked so well, why aren't we flying to Mars right now? Well, looking at it impartially, NERVA wasn't a victim of engineering failure at all. In fact, by 1968, NASA deemed it completely ready for human missions to Mars. But the post-Apollo era brought a dramatically changing political landscape. The Nixon administration had to balance competing national priorities and shifting budgets, and they ultimately decided to pivot focus toward the Space Shuttle program. Funding dried up, and this incredibly successful program was quietly shelved in 1973.
Let's jump to the present day. Section 5. Next-Gen Gas Core Reactors.
Fast forward to today, and the drive to safely put astronauts on Mars has sparked a massive revival. NASA and DARPA are currently collaborating on modern nuclear thermal propulsion. Why the sudden interest again? Because cutting down travel time is absolutely crucial. A faster transit drastically reduces the crew's exposure to dangerous cosmic radiation and minimizes logistical risks. If you can slice a 9-month trip down to just 4 months, you completely rewrite the safety equation for interplanetary travel.
But engineers want to push efficiency even further beyond those old NERVA designs. And to do that, we have to look at some extreme physics. See, solid reactors hit a hard limit. If they get too hot, the solid uranium fuel simply melts. To get around this, modern researchers are proposing these wild gas core architectures, like a multi-cell nuclear light bulb. Instead of solid fuel, the uranium is actually allowed to become a superheated gas or plasma.
It's like trapping a miniature star inside a glass bottle. Here is exactly how this closed-cycle process works. Step 1. The uranium sits in the center as a blazing 20,000 degrees Celsius plasma. Step 2. A swirling neon buffer gas isolates that plasma so it never physically touches the reactor walls. Step 3. The whole reaction is safely contained inside fused silica, or quartz walls, which let the intense ultraviolet heat pass right through. And finally, Step 4. The hydrogen propellant flows along the outside of that quartz, absorbing the radiant heat and producing massive thrust, without venting a single particle of radioactive exhaust.
2,000. That number is literally a game changer for aerospace engineers. A theoretical gas core design like this could eventually hit a specific impulse of nearly 2,000 seconds. We're talking 3 to 4 times the capability of our very best chemical rockets today. A leap in efficiency of that magnitude doesn't just make Mars a quick trip, it opens up the entire outer solar system to rapid human exploration. And finally, Section 6, the future of deep space.
Chemical rockets got us to the moon, absolutely, but their limits are clear. With the historical success of those old NERVA Brown tests proving the engineering is sound and the jaw-dropping potential of modern gas core designs, we're left with a pretty profound question. Is the mastery of the atom and the vacuum of space the key to permanently unlocking the stars? Will nuclear rockets be the technology that finally transforms humanity from a planetary civilization into a true multi-planetary spacefaring species? Thanks for joining me on this explainer, and keep looking up.